This is joint work with Aanchan, and I'm going to present a way to learn content and usage factors simultaneously to reduce clickbait and among other recommendation benefits that you get. So I work at Flipboard. If you don't know what Flipboard is, it's the world's largest content curation platform. So on Flipboard, you can follow topics, select some subtopics like that, and we'll just create a personalized feed for you using editorial and user curation, and machine learning is at its core. So currently we serve personalized feeds in English, French, and German, and we have over 145 million monthly active users. So I should mention that the recommendation problem is actually quite different from a lot of the classic recommendation problem you deal with. Like, we are at there's always cold start when you're dealing with things like news, because you can't really wait to get a lot of usage, because by the time you get usage, that article may already be irrelevant. So we do a lot of collaborative and content filtering, and I'm going to mention a bit of that. So the existing system at Flipboard does this. So we have a system that has a multi-label topic tagging system that in English we have 16,000 topics. So each document is represented over the 16,000 topics, and based on user, based on user clicks, we aggregate their users' topic affinity and then match the users with the right documents. On content filtering side, we also do things like extract source information, like do you like BBC, or do you like The Guardian, or do you like Sky Sports, and also because Flipboard has a lot of users, there's also user magazines. So we take which magazines does the user actually like. So we take a lot of these content signals into account, a lot of source signals into account. On the collaborative filtering side, we get around 500,000 articles into our system every day. We get a lot of sparse explicit signals, like likes, flips, which is a Flipboard concept of putting things into your magazine. Shares, and we also get a lot of implicit signals like views. So we do something that is pretty standard in industry. We do a classic implicit latent factor model for collaborative filtering, originally proposed by Hu, Kern, and Volinsky, that takes both implicit and explicit signals into account. But as mentioned, cold start is a big deal, so you can't just do collaborative filtering. Content filtering actually plays a huge role here, because we generally do collaborative filtering once we are pretty confident that this is a good article. So there is some minimum engagement requirement. And we hybridize, while building personalized feeds, we hybridize content and collaborative filtering using editorial heuristics and some journalistic principles. And our systems have been performing quite well, and our user base has been increasing for a while. But there are a lot of challenges, and there are some challenges and limitations to this approach. And one of them being, I'm actually one of the main authors of the topic extraction system. And working on the content filtering side, it's actually quite difficult if you want to do multilingual topic personalization, because we launched personalization for French and German, but if we want to launch it for Spanish and Dutch as well, we actually have to develop a reliable topic model with good enough quality, and that takes quite a lot of human and engineering effort. Not to mention, there's also a lot of content curation involved, and this can take a while. So the other option is, what if we just do collaborative filtering? So like I mentioned with collaborative filtering, in our domain, the problem that you get is because you're always in a cold start, you have to start collaborative filtering way too early. If you don't do any content filtering, you get a lot of high mean, high variance results. What that means is you do see a big improvement in engagement, but you also see a lot of user feedback about low quality articles. So we need to incorporate content into account, but this is the slide that will give you the high level intuition of what it's about. So if you look at the bottom half of the graph, what latent factor model for collaborative filtering is, you take a usage matrix and you're learning low dimensional representation of documents and low dimensional representation of users, and you multiply them loosely and you try to approximate the usage matrix. Now if you squint, technically you're doing a very similar thing in topic modeling. So you have a word count matrix, and you're trying to learn lower dimensional representation of documents over topics and lower dimensional representation for terms. This is actually what happens in LSI, but generally when you're talking about topic modeling, you tend to look at like probabilistic topic models like LDA, where really the only difference is that the document factors are probabilistic vectors instead of like real valued vectors. So one of the intuitions that we had, or is how about you, instead of learning two separate like document factors, how about you just learn one? If you learn one and just share the parameters, then theoretically you could say that one can help regularize the other. So that was kind of the idea, but however, there is a problem there, like I mentioned. In LDA, you're in the probability space, and in the collaborative filtering world, you're in the real domain. So how do you convert a real valued vector into a probability vector? Well, you can do something like just pass it through a softmax. And that is something I'll talk about a bit more. So why is this a good idea? Well, first of all, like I mentioned, we are always in a cold start problem. So if you can, when you don't have any usage, if you can just use the content to infer document factors, it can help you get a long way. Also, collaborative, this is also not just purely optimizing on ratings, so you can better regularize the parameters. And the intuition that, really behind all this is that the latent space of collaborative filtering and the content should be quite similar. So this is not a unique idea. Like there has been work on it, like collaborative topic regression being one of them from like Dave Bly's group, and hidden factors as topics, and Topic MF have tried to do similar things, and they've essentially just mapped this document factors through a weighted softmax. We build on that, and I'll mention, so this is a little bit different from their work, but a lot of our loss function is built on the three previous papers as mentioned, the two content CF ones and the classic implicit CF. So the two aforementioned paper only look at explicit ratings. We look at implicit. So the left-hand side of the model you see, I think that's the model most of the RecSys community will be pretty familiar with. That's the classic implicit collaborative filtering. What we are doing further is just regularizing it with a topic model. Now, notice that the topic model side, if you know LDA, it's quite similar. So the phi is still a Dirichlet distribution, Z's and W's are multinomial, but theta and the gamma D, which are the document factors from collaborative filtering side, are connected via a softmax. So yeah, what you get is this is kind of like, so the topic modeling document factor uniquely defines the collaborative filtering document factor and vice versa. And if you also squint, if you actually look at it, there's another key thing to notice here. That is, this problem is actually identical to a correlated topic modeling problem. So in correlated topic modeling, the only difference is that the theta comes from a logistic normal, which is essentially a softmax times a Gaussian prior. This one is essentially just a softmax. So this is the topic modeling side is essentially a correlated topic model without a Gaussian prior, and there has been a lot of work to optimize that. There are some references at the bottom. So the other problem with the HFT and Topic MF papers in production was that we know in the RecSys community and the NLP community that if you increase the number of factors, you generally achieve better performance in recommendation. And same in NLP, if you increase the number of topics, you get lower perplexity. However, their approach is, when they were trying to do the inference on the GIP sampling bit, it had an OK dependency. So when they were trying to sample that, their training complexity for the GIP sampling bit was OD and K. But we use something called alias sampling to optimize that further down to O1. And and that's built on a work by the Light LDA group, and I have a blog post on that as well. So if you're interested to check that out. So the intuition about like how can you sample if you're trying to sample a multinomial in O1, how the heck do you do it? Is that even possible? So the intuition is actually this. So when you're doing a multinomial sample, if you're doing it naively, what you do is you build this probability vector, you spend all this time building this table, and then you just take a single sample, and then you throw the table away. And that seems like a waste. How about, instead of when you spend all this effort building it, how about you take K samples? So you get K samples in OK time, because once you have the table, sampling is just O1. And when you have K samples, what you can do is just store those K samples in memory, and every time you need to use something, you just look up if you have some steel sample, and you do a Metropolis Hastings test to check whether the sample is still valid or not. And if you don't know, like Metropolis Hastings is, the intuition is, it just checks whether moving from state X to a state X prime, is that actually a good idea? And you compute that with this simple function. All right, so really the training algorithm is quite simple. You iterate, so you iterate between, first you do an alternating least squares on the usage matrix, then you do a few steps of Gibbs sampling, and notice that Gibbs sampling is now just ODN, so now you can train a lot more topics. So what really changes? Actually, not that much changes, really. Like the user factors are completely independent because that's a totally different part of the model. The document factors are connected to topic model, so the only thing that really changes is the initialization. If you're familiar with alternating least squares for collaborative filtering, the only thing that really changes is the initialization. So that really doesn't add anything, add any complexity to the ALS side. On the Gibbs sampling side, you actually do it via alias sampling, and we suggest switching between the document and Word proposals, like these two proposals, and you get about 45 to 50% sample acceptance rate, which brings the sampling complexity down to an amortized 0.1, which lets you train a lot of factors. Now, so there are three key results that I would like to show, like one of them being like this really helps with cold start. This is our implicit HFT model. Like if you were to observe all of the data, 100% of the data, the top right-hand corner, like the 100-100, is the best you can do. However, what we noticed, we just started to, how about you hide the data? Like if you hide like 90% of the data, and use the same model, because you're learning the factors also from the content, you can actually get 75.3% of the recommendation quality just by observing 10% of the usage, which is a big deal if you're trying to solve the cold start problem. And of course, as you get more usage, your recommendation quality improves. Furthermore, this is kind of intuitive. Like, the topic MF paper, HFT papers originally only trained on 5 to 20 factors. Of course, increasing the number of factors helps in recommendation quality, which is what we notice as well. In mean average precision at 5,000, we get 500,000 documents. So we see an improvement of about 24.3% and in mean average precision and 26% in geometric mean reciprocal rank with 128 factors compared to 15. Also, we compare to a pure collaborative filtering, which is if you were just doing an implicit CF, and if you were incorporating content into the mix, gives you about a 24% improvement in mean average precision as well. And as mentioned, so we started off by saying, hey, we need to reduce clickbait, and we actually do notice that because what we see is that we see 16% more articles in our feeds from higher quality sources as judged by our editorial team and some algorithmic work. There's another blog post here that we determine how we judge quality, and we see 16% more articles from higher quality sources using our model. So I talked a lot. The key takeaways really is that sharing document factors between usage and content helps improve the quality of recommendations and the cold start problem. Incorporating implicit signals, in industry, that's a very common thing to do. It also helps make your usage matrix a lot denser and makes you also learn a very good recommendation model. And the key thing here is, if you do O1 alias sampling for topic models, it can help you scale things like HFT to production data sets, which is what we did. With that, that's all I have. Thanks for listening. We are hiring. If you would like to reach out, just contact me. Thank you.
Thank you, Arnab. Very good presentation. So first of all, I remember I read an article, it's called the Collaborative Model topic modeling by, I think it's Chang Wang and
Yeah.
David Blake.
The collaborative topic regression.
Yeah, exactly.
Yes.
So is there any difference with what they proposed for your work? Could you elaborate that?
Yeah, great question. So like I mentioned, this is not a unique idea. So the unique, hidden factors as topics and topic MF also do propose similar things. But the key problem that they have is the second part. They're essentially doing the same thing. I think Chong Wang's paper is doing variational inference instead, but the GIP sampling bit costs ODNK time complexity. So if you're trying to train a lot of topics or a lot of factors, you can't actually do it in production data sets. It just doesn't scale. So with our work, it's just you can scale it up using alias sampling because that time complexity is ODN for GIP sampling bit. Okay, so basically the computation complexity will be kind of reduced here. Yes. Okay, second question. So is how do you determine the number of topics? What is your criteria to determine the best number of topics in your model? So that's a good question. So, because we got rid of the K dependency, why did we stick with 128? We actually tried training 128, 256, 512, and we saw that you don't see any noticeable gain. You do see a bit of gain as you go further up, but then the ALS side gets slower. So it's really about your computational, how much can you handle? And 128 factors is what we were using for our collaborative filtering model in production anyway. So yeah, I mean, wherever you get if you can train with more, why not? But what we noticed was you weren't really getting that much improvement in recommendations, so we just stuck with 128. Sorry.
So what is the criteria you use to compare, is good or not?
Mean average precision at K. So this one right here. So when we trained with 15 factors, we also trained it with a lot of factors in the middle. So I mentioned 15 because the HFT paper suggested, I think 5 to 20. That's 15 seemed like a number sort of in between.
Okay, that's good. Thank you. Yeah.
Hello.
Oh, hi.
Yeah, we're here. So you described part of the benefit of your model was reducing clickbait, and there's a lot of people trying to reduce clickbait out of many places, right? So it's not obvious to me, besides sort of the way that you're correcting for the popularity bias by basically introducing the content regularization, how you are implicitly modeling clickbait, right? So is the clickbait reduction just a consequence of reducing popularity bias, or is there anything magical there in your model that you feel like it's learning what clickbait means?
No, I think that's a very good question. It's actually the former, really. So it's the problem is that when we are just learning on the usage matrix, because we are doing it way too early as well. So we almost feel that the model that's learning, we are only learning the popular articles, and if you don't take content affinity into account, you end up just getting a lot of clickbaits. But no, I mean, I don't think we really learn any kind of internal representation of what a clickbait is, but essentially we are just trying to use the content to regularize the popularity.
Yeah, makes sense. Thank you.
Yeah.
Thank you for your talk. Working in also the news, I understand one of the main focus was about this cold start things. But in a term, go back to clickbait and a bit related to the previous questions. So the kind of signal you're using will be kind of, well, it's click, but often in the news industry, you use dwell time as a way to reduce clickbait.
Yeah.
So have you considered this? Because maybe it will have just worked by using dwell time with respect to the content aspect.
So technically, we actually take everything into account, and even with if your usage matrix, actually this usage matrix is not just click.
Okay.
Technically, it's if we take view time and display time into account, but even then, you will still end up getting a lot of clickbait because from what we, at least in our experience, if you were just to train based on view time, or even just if you train it based just on view time, you get a lot of clickbait. But there is something that you can trade off. If you train it on higher quality signals like likes and shares, you might get fewer, but at the same time, then your model, gets very sparse. So there's a bit of like trade-offs to do there, but I think we have found that if you just train it on view time as well, you still get a lot of clickbait.
It's not on its own. It's a combination. It tries to it kind of normalize the click indirectly. You cannot use it on its own. I can't say more, but yeah.
Yeah.
Anyway, thank you.
No worries.
Excellent. Thank you, Arnie.